In this problem, the Empire is testing a new ion engine. It creates a very strong acceleration, but it rapidly decays because it runs out of fuel. So we're given the acceleration function 200 e to the minus 0.01 t meters per second squared. They strap this onto a test ship that's already going 100 meters per second. They turn it on, and what happens? Basically, how fast is it going after 150 seconds? So for this problem, you can't use your memorized kinematics equations because acceleration is not constant. In some problems, when acceleration changes, you can still use them, like in the Super Karate Monkey Death Car problem. It was accelerating at one constant acceleration for a while, apply your kinematics equations, and then a different acceleration for a while, apply your kinematics equations. But here, it's continuously changing in time, so you have to use calculus. Now, what does that mean, use calculus? Well, remember, you have position, and then you have velocity, and then you have acceleration. And to go this way, down, it's derivatives, and to go this way up, it's integrals. So you got to look at what you have. You have acceleration. It's unlikely you're going to need to take a derivative of that, because there's nothing down there that we're usually interested in. You're probably going to want to go this way. You're given acceleration, and you're asked for the velocity. So you probably need the one where you have to do the integral to get from acceleration to velocity. And in fact, if you know your calculus, that is that delta v is the integral of a dt between 2 times t1 and t2 for delta v1, delta t2. So let's apply that to this problem. We're going to go from t, what we'll call t equals 0, when the engine was turned on, to t equals 150 seconds. Okay, so what does that mean, delta v? Delta v there then is the v at 150 seconds, the one we're looking for, minus the v at 0 seconds. Well, that's 100 meters per second. It had an initial velocity. That's like vi. And then here we need to integrate from 0 to 150. And now we got to put that function in. 200 e to the minus 0.01 t dt. All right, so let's see. V at 150, the one we're looking for, minus 100, that's the initial. And to integrate this, it remains e to the minus 0.01 t, and you divide by the derivative of this with respect to t. So you're going to divide this by negative 0.01. So it's going to become negative 20,000. 200 times 100, 20,000. Negative. Okay, and then it's e to the minus 0.01 t. And now that we've taken the integral, we've got to evaluate it from 0 to 150. All right, I won't write that side again. I'll say this is equal to, and I'm going to do, before I evaluate it, I'm going to pull out the minus 20,000. And then here in parentheses, we'll say e to the minus 0.01 t, where t is 150. That is, I did it about 0.22. And then minus, plug in 0. E to the 0 is 1. So you can see evaluating that integral gives you the negative sign. A negative number takes care of that negative. So it does come out positive because you would expect the velocity to increase positive. Numerically then what we get is that v at 150 minus 100 equals, this comes out to 15,537. And this is all in meters per second. So in the end, we got to add on our little initial velocity. It didn't make much of a difference. 15,637 meters per second. Rather fast. And the acceleration was rather hard. If you think about it, at time equals 0, the initial acceleration was 200 meters per second squared. So I hope there wasn't anybody in this test ship. Then again, it was the Empire, so there probably was.